Yes, so hello friends, this is the video tutorial for today's GFG problem of today, second best minimum spanning tree. So what the question says is that you are given some edges in the given some edges in the graph. So edges basically meaning 0, 1, 4 basically meaning that there's an edge from 0 to 1 which has a weight 4, 0 to 3 means that there's an edge from 0 to 2 which has an edge 3. Okay. So you are given these edges in the graph and you are also given the number of vertices, which is V. I'm using N here. So basically N and V are used interchangeably. Your task is to find the weight of the second best minimum spanning tree of the given graph. Second best MST is defined as the minimum weight spanning tree whose total weight is strictly greater than the weight of the minimum spanning tree. If no such MST exists, return -1. So whenever you encounter an MST problem, you should always think of two algorithms. One is the Prim's algorithm, which is pick the least, which basically means that let's be greedy here. Let's keep two two components. One is the connected component, another is the disconnected component or not connected component, and we'll always pick a least edge, which is from this connected component to the not connected component. Here, this problem I don't think can be solved using Prim's algorithm, so we'll use Kruskal's here. But Kruskal's basically means in Kruskal's what we need to do is sort the edges and pick the smallest v minus 1 such that they do not form a loop. So what is why do we need to pick v minus 1 is basically this is a graph, so this is a tree property. So what's the difference between a graph and a tree is that in a graph there can be any amount of vertices, there can be any amount of edges. Graph can be connected, graph can be disconnected, but for a graph to be a tree, so there's a graph subset, tree is just a there's a graph set, tree is some such subsets of the graphs, right? So for a graph to be a tree, it should have v vertices and v minus 1 edges. And the criteria is that there should be no loop. So even if like this graph, I can say that this graph has one, two, three, four. So four vertices and three edges, right? There's three edges here. But this is not a graph because there is a loop and this is not connected. So this is not a tree rather. So for a graph to be a tree, this has to have no loop. And if it does not have a loop, so let's say we remove this edge and add it here, it would become connected because we have v edges, v vertices, and there are v minus 1 edges which do not lead to a loop, so it would become connected. So this is what a tree is. Now how do we get from a tree to an MST is that a given given graph, let's say this graph has like if so this graph has some E edges, right? We have to pick some V minus 1 edges from it. From E edges, we should pick some V minus 1 such that this graph gets converted into a tree. The rest of the edges will remove, right? So given this graph, the MST is something like this. So now we can see that this had some cycles. This had this cycle, this cycle. Now these cycles are getting removed and we have picked V minus 1 edges. So here, this graph had how many? One, two, three, 5 vertices and 6 edges. Now we have converted into a 5 comma 4 3. So 1 2 3 4 5, right? So to do this, we, as I said, we have two algorithms, Prim's and Kruskal's. We'll run Kruskal's here. So how we did this conversion is using Kruskal's. So Kruskal's basically means that, okay, Kruskal's basically says is first let's sort all the edges. So we did this. We sorted the edges in the graph. So this has these 1, 2, 3, 5, 6, 6, right? This is the sorted edges in the graph, sorted by weight. Then we'll pick the first edge. Okay, we pick the first edge. We pick this thing. Let me try run this again. So just to understand, make you understand what Kruskal's basically says. Okay. So we make add this one, this edge one in our graph. Then we add this two edge. So we pick this two edge. Then with this three edge, then we pick this three edge. Now when we pick five edge, five we should not pick. Why we should not pick? Because five is creating a loop. If we pick this five, one sec. If we pick this five, this will create a loop. So we should not pick this edge. Okay, so we don't pick this edge. Now we go to six. Now this six is this six. Now we have seen that we have picked 1, 2, 3, 4. So we have picked four edges and we needed to pick four edges because the number of vertices is 5. So what is the MST cost? MST cost is sum 1 plus 2 plus 3 plus 6. So that is 1 plus 2 plus 3 plus 6. That is 12. right? Yeah, 12. So this is a dry run of crystals. Okay. So we understand what crystals is, but how do we use crystals to find the second best MST? Now the criteria for the second best MST is that the cost of the best MST, the cost of the second best MST should be greater than this, and it should be the minimum because it is second best, right? So it should be the minimum value that is greater than the best MST cost. Okay. So how do you do this? See, when we do our crystals on the graph, we get the best MST cost, and we also get which vertices we are picking, which edges we are picking. So here we get these two things, right? We get the edges picked, that these are the edges that we picked when we did the crystals algorithm. Now, how many vertices would we, how many edges we would pick? As I saw in the graph, we need in the three we need v minus one edges, right? So this would be v minus 1, v, and I'm using interchangeably, so this is of the order n, right? This is of the order n. Now let's say what we need to do is get the second best MST, right? So we know that the best MST will have these vertices, these edges, sorry. So can we do this? Let's remove the first edge from the graph, and now let's get the MST cost. Okay, let's call this MST2. Okay, this is one thing that we can do. Now let's keep this edge and let's remove this edge, the second edge. We keep this edge and now remove this. We get another MST cost. Let's keep these two. So basically what I'm saying, let's iterate over the edges picked, let's remove them one by one, and let's get the MST cost. So we'll get some MST2, right? Some MST2. Now what is the minimum thing that what is the criteria on this MST2? Would this be greater than equals to the best MST? Obviously, if we had all the edges, we're getting best MST. Now we have removed one of the edges that was in the MST. So on removing this criteria must be satisfied, right? Because see, if you were getting, where's my pen here? Okay, what happened? Where's my pen? Uh, okay, this is weird. Okay, check. Okay. So for 10 edges, if you were getting an MST cost of, like, let's say 12, with 9 edges, how is it possible that you will get 11? This is not possible, right? With 9, your value would be, it could be 12, it could be 13. Now, if it is 12, like it could be 12 or greater than 12. Now, if it is 12, it cannot be a second best MST because the criteria is it has to be greater than this. If it is greater than best MST, then we'll store it in the second best MST. Okay. So yeah, what would be the time complexity of this approach? So these edges picked is of the order n. So n into how much time uh, does the Kruskal's algorithm take? It takes e amount of time. E here is like the maximum value e could be is n square, right? That is the graph is fully connected. That each node is connected to in every other node, so that is n square. So this is n cube, and in the n is of the order 10 square, so this is 10 raised to power 6, which is very much fine. We can also say here that the number of vertices is of the order 100. So if this makes sense, let's jump to the code. I won't explain what the DSU is. I will leave some articles on I can explain what DSU is, but I won't explain how we implement DSU. You can look up some articles. I will also leave some use Sacco guide articles, and yeah, that would help you. So yeah, let's jump to the code. So first I created DSU objn. So I will give a bit of explanation of what DSU does. So in my implementation of DSU is basically disjoint set union. So if you create a DSU objn, what I'm basically saying is let's create a data structure of n values. These values are from 0 to n minus 1. Now I will have some functions on it. I will have like, so basically what a DSU is a, like, will have some sets of values. So, let's say the first set of values 0 1 2, the second set of value is 3 4 5. Now these set will not have any common values. That is, they are disjoint sets. Let's say this is 3 4 and there's another set 5 here. How to implement it, I won't go through it, but I am just giving an example of what disjoint sets are. Now If I say that I want to unite 1 and 4, that is the set that has 1 will get united with the set that has 4. So this would become that these two gets combined into 0, 1, 2, 3, 4. Okay. And it also has some checks, like we can check that are these two values in the same set or not. So why is this important here is in Kruskal's, when we do a Kruskal's algorithm, our graph could become this disjoint sets only. So there's one set here, there's one set here. So it could be that the graph is in the state like this. So 0, 1, 3, and there's a 2, 4, 5 here. So let's call this set as set 1. Let's call this as set 2. Now, if we are picking, we get this edge. Should we pick this edge? How we will check is that this should not cause a loop. When would it cause a loop? If the two edges that we are connecting, if the two vertices u and v we are connecting are in the same set. If they are in the same set, we should not pick it. If they are in the different set, we should pick them and then unite these two sets. This is how a crystals get implemented. Again, this is a brief overview. Look up some articles, look up some videos on how to implement DSU and how to implement crystals using DSU. So the first thing that we need to do is sort the edges. So that is what I'm doing here. I'm sorting the edges by the weight. So using this custom comparator, I'm sorting it using the weight in the ascending order. Now I calculate my best MST value. So this is just a brief, this is how we run crystals here. So count is basically the number of vertices that we have picked, number of edges we have picked. If we have picked n minus 1, we can break here because we do not need to pick more than n minus 1. Then and then this is u. There's an edge from u to v which has a w weight. If uh, picked edges dot push back, this should actually be here. Okay, I actually submitted the wrong code. It's still got like this time complexity of this would be e raised to n raised to power 4. So I don't know why this got submitted, but this should be a picked edge pushback. I guess it should come here. Okay. So if the U and V are in the same set, we will not pick this edge. If they are not in the same set, we'll pick this edge. So we added it into the picked edges array. Then we united this U and V. I incremented my count and I added them to best. Like this is the best MST cost. Now we'll calculate the second best MST cost. So I go over all the picked edges. I remove them from the graph. Again, removing it from a graph is a bit complex. What we'll do is just go over all the edges, and if this edge is the same as this removed edge, we'll just continue. That this is we should not pick this edge. Right. Again, we do the same critical traversal. I go over all the edges. I see if count is n minus 1. If it is, we'll break. If these u and v are in the same set, or this is a removed edge, we'll not do anything. We'll continue. Else, we'll pick this edge. We'll unite uv. We'll add it to our answer and count plus plus. Now we'll check here. If count is n minus 1, so we were able to get a MST, and we'll check if its cost is greater than the best MST cost. If it is greater than the best MST cost, we'll add it into a second. Now we'll check if second is int maximum. So if it is int maximum, we were never able to get a second best MST, then we'll just return minus 1, else we'll return second best. We'll submit this. The GFG test cases are a bit like weak, so that is why I think like in raised to power 4 solution got accepted. So what I was doing here, let me show you. If I do this here, picked edges dot pushback I, like we saw here, why this solution works is because the edges picked is of the order n, because the number of edges that we'll pick for a Kruskal's algorithm is v minus 1 or n minus 1, that is or of the order n. But if I do this here, I'm even adding those edges that are in the same subset, so this could become very large, like almost all the edges could get picked. So that is why this is n square, so this should actually be here. So if this becomes n square, then this loop will n square run n square time, and this is already n square. So that is good. This is n ratio by 4, but like that solution also got accepted. I don't know why. GFG test cases are a bit weaker. That's why people prefer lead code and code forces and code have those platforms. So yeah, this is it for this video. If you like this video, if you like the explanation, if you were able to understand anything, please drop a subscribe and all of those things. Bye bye. Thanks for watching.